All right. I can describe and apply the mole concept in Avogadro's number by being able to convert among moles, mass, atomic numbers of atoms in a given sample. Okay, that sounds really intimidating. It's actually not. But let me unpack it for you a little bit. So today we're just going to unpack it with the help of Hank Green.
It took an Italian house elf, genius, Lorenzo Romano Amadeo Carlo Avogadro di Guarania e di Ceretto. I did the first time. We'll just call him Amadeo Avogadro, but he was a count, so he had to have a super fancy name, and I'm me, so I had to try to say it. Much like Lavoisier, Avogadro's political alliances would get him into trouble. After Napoleon's downfall in 1815, Avogadro was active in the Italian anti-monarchy revolution, possibly even sponsoring some revolutionaries with his personal fortune. For this, he lost his chair at the University of Turin, but thankfully he did not lose his head. Avogadro proposed, correctly, that any gas in a container of the same size with the same temperature and pressure would have roughly the same number of molecules in it, no matter what the gas was. So any difference in mass between two flasks of the same size full of two different gases would be because of a difference in the actual physical mass of the molecules. And thus, Avogadro basically figured out how to weigh atoms and molecules, as long as they were gaseous. To support his hypothesis, which was certainly good enough to support, he suggested that in forming water, oxygen gas would actually split into two oxygen atoms, what he called elementary molecules that could not be broken down any further. For some 50 years, Avogadro's idea of fundamental molecules were ignored, maybe because of incorrect ideas about how atoms stuck together, maybe because Italy was a bit of a backwater of science and Avogadro wasn't considered an important thinker at the time. But the scientific community, as it usually does, came back around to Avogadro's ideas eventually, not only naming his proposal that equal volumes at the same temperature and pressure contain the same number of molecules, Avogadro's law, but also giving him his own number. Maybe the most important number in chemistry. Certainly one of my very favorite numbers, but we'll get to that later.
All right, so in chemistry our job is to sell atoms. Can we use the same concept to do just that? Where can we find the list price for all the elements on the periodic table? That's right, Ruth, as she reaches for her periodic table. Yeah, on the periodic table you can find the price list for all the elements, right? How do we measure the mass of atoms? Well, they're so teeny tiny. Can we use grams? No, we use atomic mass units. Or just use, right? But what is the problem with measuring things in AMUs? Well, we don't have a device that can measure in AMUs. AMUs is too small a device. Our devices measure in grams. That's how we measure, in grams. So, let's measure in grams. But holy cow! If we're going to start measuring in grams, we're dealing with things to the negative 24th of a gram. Try having to mess with that all the time. So it is not practical to measure the mass of atoms. We have to find a way. We have to find a way to measure atoms using grams. There are many words in the English language that we use to describe a certain number of things. If you lay eggs, you lay them by the dozen. So if you lay eggs, every night you lay 12 eggs. We're used to that. Chickens lay so many eggs, they stop counting. They just say, hey, I have laid 6 dozen eggs already this year. Okay? So they go by dozens. Eggs are too small. Can you go to Staples and say, hey, I'd like to purchase 56 sheets of paper? No. They're going to look at you and go, you can buy a ream. I don't want to buy a ream. I want to buy 56 sheets of paper. Well, you can buy a ream and then throw away the other 444 sheets and just keep the 56. No, I don't want to. Too bad. You have to buy it by the ream, 500 sheets. So do you think that paper companies come up with the number of sheets that they create every year. No. It's a whole lot easier to come up with the number of reams. Reams. What about gross? If you ever see somebody take their finger, stick it in their nose, and then stick it in the mouth, then what do you have? You have the number 144, right? 144. So the next time you see that, go look at them and go, 144! 144! Why? Because that's what gross means. So stop saying, now you need to use the word disgusting, because disgusting is not a number of things. Icky! Don't do that. Icky! You're going to get Ebola that way. It would be impractical for a jelly bean company to keep track of every bean that is produced. In the same way, it is impractical to measure a few atoms at a time in grams. But what if you had 1 trillion atoms? Is that enough? One atom, can't see it, can't measure it. How about 100 atoms? Can't see them, can't measure them. 1,000, is that enough?
No.
1 million, is that enough?
No.
1 trillion?
Yes.
No. 1 bajillion? No. How about a 602 sextillion?
Yes.
At that point, at that astronomical number, you finally have enough on your scale that you can measure. Who worked out that number for us? Or actually, he didn't work it out. He helped us get to the point where it was worked out. An Italian scientist by the name of Amedeo Avogadro. What did Avogadro's number help us come up with? A way of converting grams to moles, moles to grams. A way of converting, a way of measuring these things enough so that we could actually measure them with a balance scale. Let me explain it to you using this video.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sextillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sextillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sextillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sextillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it. The story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
So, a mole of carbon is how many? All you have to do is look on the periodic table and find its mass. 12.01. That's it. A mole of lead, look it up, 207.2. How many molecules of lead do you have there? How many atoms of lead? 6.02, and they weigh 207. How about a mole of silver? Look it up, 107.9. A mole of copper, look it up. A mole of silicon, mercury, sulfur, and iron, nails. Look it up. Why did I teach you formula mass? Because a mole of nickel chloride look it up. Add them up. What is this? 58.5? 0.7? 58.7? And then 35.5 times 2. Add it up. Bam. That's how much you have there. So if you want to know how much all these things mass, all you have to do is look it up. Add it up. So how big is a mole? 6.02 times 10 to the 23rd. How many iron atoms do you have in a mole, Molly? How many atoms? How many eggs do you have in a dozen? How many atoms do you have in a mole? Times 10 to the 23rd. Now, Molly, how many grams do you have in there? 55.8. How many mole in a mole of oxygen molecules? Sasquatch. How many oxygen molecules? What is the mass? Wrong. Wrong. What? Sasquatch? No. Phoebe, how many? What? 23? Wrong. Simon?
What? 32.
32. Folks, remember a couple of weeks ago, I asked you to remember. And I told you, this is going to become important in the future. I told you to remember that there are 7 elements that when they're in their natural state come as a twosome. They are?
Diabolical molecules.
Brother Huncliffe. Diatomic molecules, not diabolical.
Diabolical molecules.
You have to remember that. You must, or else you're going to get these wrong. There are so whenever you're dealing with just elements, is it one of my 7? No, then just whatever the periodic table tells you. Yes, multiply it by 2. Well, I rounded up from 55.8. Look at iron. 55.8. Yeah. Okay, so I've got a carton of eggs here. You know, there's more information here than just the fact that it's a dozen. 1 dozen. Okay, they tell you, just for those of you who may not know, they tell you there's 12 large ones in here. If you're asking, well, large what? Well, come on, they're eggs. Okay, there are 12 large in there. You know what else they tell you? They tell you that there are 24 ounces, which I converted to 0.709 liters. 0.709 liters. So they told you the volume, and they told you the mass, which is 681 grams. So if I was to, if Gup's mom was to say, hey, Gup, Morgan, go and buy me 681 grams of eggs, what would she do? She would go and buy a dozen eggs. Because, a dozen large eggs. Good. Because they are synonymous. These things are an equivalency. They equal each other. They're things that we could now add to the back of our periodic table. You understand? So what does that mean? That means we can use them in factor labeling. Okay, so eggs are not very important to us in chemistry. What about moles? A mole of carbon, just like a dozen eggs, is... Well, if eggs is 12, a mole is 6.02 times 10 to the 23rd, right? Mass, well, whatever the mass is... Yes, Delaney? I don't know. They've already come and picked it up. I don't have any more bottles. I'm sorry. I know. I'm sorry. Bye. Okay, for carbon, it's 12. If I was to say a dozen donuts, it would have a different mass, right? For carbon, it's 12 because that's what it is. It's on the periodic table. Now, the interesting thing about the volume is that Avogadro really didn't give us 6.02 times 10 to the 23rd. He actually helped us understand that it did not matter what gas you were using. If you stored them at the same temperature and pressure, then they were going to have the same volume, if they had the same number of molecules. If you have the same number of molecules, it didn't matter what the gas was, it was going to have the same volume. Eventually, that helped us understand that in 1 mole of any gas, of any element, you would have 22.4 liters. So unlike here, where a dozen eggs is 0.709, but a dozen donuts would have a different volume, and a dozen roots would have a different volume, in chemistry, a mole of anything has 22.4 liters. Now, that's kind of confusing. And some people just don't understand. Some people never understand this concept. So back when I started teaching, I got so frustrated because I could not teach this concept that I developed the no-think system. Okay? And this was a way of training kids to robotically be able to come up with the information they needed in order to answer all of these questions. Okay? In order to be able to at least create the relationship without understanding the relationship. So there was no thinking involved, it was just robotic memorization. Okay? That's the way they teach in the Army. If you've got a sibling in the Army, Navy, Marines, there is no don't think. You just they will train you to take apart your weapon, and then so well that you can do it in the dark. And you don't really understand all the different pieces of the weapon, but you can take it apart and put it back together. All right? So this is how I teach it. When you see the unit, mole, you 1. What does that mean? Don't worry about what it means. When you hear that annoying noise, which all it is a high-pitched, high-frequency way of saying think. Think! Get it? That's all I'm doing. All I'm doing is saying think! But it really seems to grate on some people. The only way you can stop me from making that annoying noise is to very quickly say what you should be putting down. For example, formula unit. Formula unit is synonymous with molecule. Now, those of you who are writing things down, look on the back of your periodic table. That's fine. What does it have? What do you have right in the middle?
Probably the same chart.
Okay. Now, formula unit is synonymous with molecule. So when you're referring to the smallest subunit of an ionic compound like sodium chloride, you would say formula unit, or FU for short. Okay? Now, some people snicker because FU may remind you of something else, so I want you, in order to avoid any of that misunderstanding, every time you say FU, I want you to show respect by saying FU, Mr. Moreno. Okay, and that'll let me know that you're showing respect to me. All right, so formula unit, or FU, Simon, is synonymous with molecules. They're the same thing. And for both of them, whenever you see FU or molecule, I want you to the number N. What is N? N is the abbreviation for 6.02 times 10 to the 23rd. So instead of saying 6.02 times 10 to the 23rd, you just put down N, and everyone in chemistry understands that N stands for 6.02 times 10 to the 23rd. Grams. When you see grams, you guys are not being very fast. Formula mass. So you just, when you see grams, look up the formula mass in the periodic table. Liters at STP. If you don't like, Noah, if you don't like that annoying noise, you're going to have to say it really loud. Ready? STP stands for standard temperature and pressure. And that's very important that it's there. But Phoebe, it really doesn't matter anything to you yet. It will in March. But for now, STP is a motor treatment, an oil treatment, as far as you know. Atoms. Number of atoms in the formula times N. Ions. Now, after a while, what happens is you are in such a desperate need to avoid having to hear that obnoxious noise that it pops into your head very quickly. And that allows you to do these things. All right? All right, Natalie, you can do the first one with me. 1.5 moles. By the way, the abbreviation for mole is MOL instead of MOLE. Okay? Hey, you're going to use that so much that I'm probably saving hours and hours of time by letting you drop the E.
That's really funny.
Okay? Natalie, what unit are you converting from and needs to be down here in the denominator? What unit are you converting to and needs to be on the top? Which is the abbreviation? What? Excuse me? Thank you. All right. So, you ready, Natalie? Mole. She wasn't fast enough, was she? FU, Natalie. Okay. I want you to take out your calculators. Take out your calculators now. Because we are going to program your calculators so that every time they see the letter N, the calculator itself knows what number we're referring to. All right? So, input into your calculator 6.02. 6.02. Now, we need to do the exponent. For most of you, it's second comma. So, after putting down second comma, you should see a little e. If you have a different calculator, I don't know, I'm sorry. You're just going to have to figure it out on your own. All right? Then hit 23. So your calculator should now say 6.02 little e 23. Does it? Okay, now let's tell it to memorize that number. So go to the lower right corner and find a button called STOW, which is short for store. When you hit it, it should give you a little arrow. Oh, I'm sorry, lower left. Lower left. Do you have the arrow? Now, for most of you, if you hit the buttons alpha, log, it'll give you the letter N. Alpha, log will give you the letter N. Do you have 6.02 little e 23 arrow N? Hit enter. Now, from now till either your math teachers show you how to erase your memory or till you remove the batteries, every time you hit alpha N, your calculator will remember 6.02 times 10 to the 23rd. So let's try it. 1.5 times N. Back to you, Natalie. Okay, did you forget something? How many sig digs? And now how many sig digs? Natalie, what unit? N is a number. What unit? Thank you for showing respect to me. Correct. F-U, Natalie. All right, Grant, how about mass? 1.5 moles of silver nitrate. I want you to convert to grams. So where do you put grams? Top or bottom? Bottom goes. Okay, so when you see mole, you... He wasn't very fast, was he? 1, when you see grams, you... All right, so what you're going to have to do is find the formula mass of 107.9, 14, and then 16 times 3. Go. Some of you get it. You understand it? So you're going, well, all right, I got it. I'm getting bored. This is called worksheet 7.3. You may want to make this correction because it doesn't say 7.3. I'm sorry, it's worksheet 7.2. It's due tomorrow. This is worksheet 7.2. Grant, 107.9 plus 14 plus 16 times 3. What is it? 169.9. Correct, Grant.
Amen.
All right, Grant times 1.5. How many sig digs? I don't think you can round up 250.8 up to 260. Unit? Questions? Yes, Ryan.
Where do you get those numbers at the bottom?
From the periodic table. All right, well, the answer is 3.3. What's the question? Marielle, let's make believe this is exactly 40 grams. All right, what are we converting from? What unit goes down here? Well, how are you going to be able to get rid of, you're trying to get rid of grams. Okay, and what unit do you need? You ready? Grams. Think! You weren't very quick. And what is the formula mass for carbon? And is carbon one of those diatomics? Is carbon one of the ones that comes as a twosome? No. Okay, so what is the formula mass? All right. Ready? Mole. Think! I'll just keep making that obnoxious noise until you come up with the answer. All right, you got it. 40 divided by 12. Good. Good.
I got you.
All right, Ryan. Let's start with, let's make it exactly 100 grams, so we have 3 sig digs of MgSO4. What unit do we need to get rid of? What unit do we need? Grams.
The mass formula.
Okay, you're not going to get away with that mass formula. Next time. All right, so.
Not yet.
Mole. 100 divided by 120.4.
8.830.
Unit. Bam. 4.59 moles convert to molecules. Ruthie.
Mole.
Goes where?
Right there.
And what goes on top?
Molecules.
Ready? Moles.
1.
Why were you cowering, Ruthie? I mean, I'm not hurting anybody, am I? Molecule.
N.
You guys are no fun at all. 4.59 times N. Go. Ruthie.
4.59 times N.
Mm-hmm.
Almost there. 2.76 E 224 molecules. Why is it 224?
That's what, well, it's going to be a big old hunkin' number because this is 6.02 times 10 to the 23rd. And you're multiplying it by almost 5. Because when you multiply it, you actually gain another magnitude. All right. Now, if you're working on your homework, stop right now because we're going to do a couple of harder ones. Find the volume of oxygen gas with a mass of 45.3 grams at STP. Maxine, 45.3 grams. What unit are you converting from?
From grams,
To?
liters,
Okay. Grams?
formula mass.
What is the formula mass of oxygen gas?
It's 16, isn't it?
Ah!
32.
Is oxygen an element?
Yes.
Is it one of our 7 elements that comes as a twosome?
Yes.
It's one of those diabolical molecules. Monocles. All right. Liters. Bang! Waited too.
22.4.
All right. So 45.3 times 22.4 divided by 32.
Uh, 31.7.
Excellent. All right. Here comes perhaps the hardest one. So please focus. Find the number of ions in a 4.08 mole sample of aluminum hydroxide. Morgan, have you done one yet? They say no. Good. 4.08 moles. Gup, I'm going to help you through this one, okay? Aluminum hydroxide. What unit are you converting from? And that goes where? What unit are you converting to? You ready, Gup? Ruthie wants you to be ready. Ruthie does not like this sound. You ready? Moles. Ions. All right. How many ions in the formula? Go. Springtime. Easter. Do you ever eat the little peeps? You know, they come in packages of 4. Okay, you know what I'm talking about? So, I mean, you can't go to the store and buy a peep. No, you can't just buy an individual peep. They come in sets. Really? Stop. Okay. All right. But if you go to Publix, you're going to find it in a package of 4, right? Or maybe 3, or maybe 2. Ionic compounds are like those peeps. They come in packages, but there are individual pieces inside of that package. So aluminum, I'm asking you for how many pieces of, how many ions in aluminum hydroxide. So let's take it apart. There's this peep, right? And then how many hydroxides? So, how many peeps in a package of aluminum hydroxide? That's how you do those. Keeping in mind that ions can come in smaller subgroups, right? Here is a group, here's a group, here's a group. Okay, let me change the question. How would that change the way it's set up? I'm going to change the question to atoms. How many atoms do you have in that package of peeps? Keeping in mind, Morgan, that sometimes ions are groups of atoms put together in a package. No. No. It is 1, 2, 3, 4, 5, 6, 7. Na2SO4. How many ions? One, 2, 3. How many atoms? 2, there's 1 right there, and there's 4 right there.
Yeah. So that one. Okay, that makes sense. How do they turn on?
How about this one?
Oh.
How many ions? Simon?
3 ions.
3 ions. How many atoms?
Let's see. 15.
2 times 4 times 2 is 8. So that's 10. 11 plus 4 more, 15.
Yep.
4.08 times 4 times n. Go, Gup. Gup. Calculator. There you go. Thought for a second there she was going to try to do it in her head, which would have been really cool. I can't do that. I had a student once, his name was Ryan Liu, and you would give him something like that, and his eyes would glaze over, and he would give you an answer that was pretty dang close to the calculator. He could estimate.
Ryan Thomas?
Ryan Liu, not Ryan. No, not Thomas. Liu. So after a while, so everyone in that generation of kids, all I would say is, okay, can you Ryan Liu it? Which meant do the math in your head. And everyone would understand because he could do some pretty heavy-duty math in his head. Gup, 4.08 times 4 times alpha log.
9.82
Units? One more question. Find the mass of a sample of nitrogen gas with a volume of 36.7. Esther, Ishtar, let's go. Liters. And what is the formula mass of nitrogen gas? What is it? 28, because Esther remembered that nitrogen is one of the brother Huncliffes.